we started looking at, well, we almost finished looking at the Unruh effect. This is in two-dimensional flat space-time. So, remember we've got two bases. So phi k are just our positive frequency with respect to the global Cartesian time coordinate. And then we define some other modes. Which are proportional to what is effectively the proper time of real observers. And we want to see, so this defines some vacuum, Minkowski vacuum, and this defines some other vacuum state, called the Wheeler vacuum state. We want to get the probability of transformation between, this is in, for x, in the right Wheeler wedge. So this is two-dimensional flat space-time. Where these are the Wheeler horizons, and this is a Wheeler observer. And you can find similar modes in the left Wheeler wedge. We want to see whether the two vacua are equivalent, or this one contains particles created by the operators that create particles, Minkowski particles, or vice versa. This guy contains Wheeler particles. So for that, you want to get the probability of transformation between them and see if this, written as a linear combination of this and the complex conjugates, indeed requires any complex conjugates. If it does, there's particle creation, and so you don't have the same vacuum state. So the way we're doing it is by noticing that this Minkowski, these are Minkowski, positive frequency Minkowski modes. You can take a linear combination of these guys with positive frequency and get another positive frequency mode. We don't call it positive frequency Minkowski mode, these are the pure modes like this. But you can do a linear combination of this. You can do a linear combination of this to get this would be positive frequency. Also, with respect to ddt. The smart insight by Unruh is in noticing that whenever you have either these modes or any linear combination of these modes are analytic in the lower t-plane or u and v planes, and they're also bounded in the lower t-plane or equivalently lower u and v planes. Okay, so this is positive. So positive frequency with respect to ddt is equivalent to bounded in the lower u and v planes, and also analytic in the lower u and v planes. Clearly, this is analytic in the. Is it analytic only in the lower planes or in the upper plane as well?
stayed all the time.
Why?
I don't see any restriction in the coordinates.
That's right. It is analytic in the whole plane. It is analytic in the whole T plane.
Eta is divided in two planes. Analytic in one or analytic in other. Is that hard or too hard?
Why is it not analytic in the whole plane?
Well, there is a difference in the T. There is two definitions for T. Yes. I mean the correlation between the coordinates T and eta and psi, they are like steps. So the one is positive, the one is negative.
Yeah. Okay, but what if this? Why is this not analytic in the whole plane?
This is the right. They are.
Is this analytic in the whole T plane?
I would say it isn't because there isn't analytic in the whole plane.
Why is not?
Because the eta is proportional to the logarithm of v over u. So there is a problem with u equals 0, and there is another problem at v equals 1 or v equals 0. Branch to the problem second in the last lecture.
Okay, so this is the value. It's proportional to this in the right wedge. It's equal to 0 in the left wedge. So there's no analytic function that allows you to do this. If you have power series expansion, which includes the left, it tells you that all the coefficients in the power series expansion have to be 0. If that radius convergence includes the right wedge, all the coefficients in the power series expansion cannot be 0, and so it is not only the power series expansion. About this point, which includes around which we get somewhere in the right wedge and from the left. What about the the negative frequency modes, are they analytic in the whole T-plane?
Oh, so yes, then yes for Minkowski.
Yes.
Are they bounded in the whole U-plane, T-plane?
T is a real number, right?
No.
No,
When I say T-plane, I mean complex T-plane.
oh, sure. Then no, there is a value of T that is converge.
What value is T?
Any complex value of T that is y times a positive constant. No. The other way. Minus y times a positive constant can make
Sorry, say this again. What value is T?
minus y minus I times some positive constant.
1.
Sorry?
1.
So huge positive constant.
1,000?
Let this thing go to infinity.
So which value of T is it that diverge?
There is no finite value of T that makes the diverge.
Right. So it doesn't diverge with any value of T. It's just unbounded in the lower plane. As T increases, the mode increases without bound. You can't say that phi k star is less than certain value in the lower T plane. You can always find the value of T such that it's larger than that value, so it's unbounded. That's different from saying it diverges with certain T values. Okay, so this guy is analytic, satisfies this. These negative frequency modes do satisfy this, but do not satisfy boundedness. Also, if you construct any linear combination of the positive frequency modes, because they decay exponentially as t goes, as the imaginary part of t goes to infinity, to minus infinity, it means that in the lower t plane, this is going to be uniformly convergent. This integral is uniformly convergent in the lower planes. And so the result, the integral, is analytic. In the lower planes. Okay, that's not going to be the case if you include phi k star, any negative frequency modes. Because those modes will blow up in the lower frequency, lower t plane, and so you won't get convergence as k. You won't get uniform convergence in the integral, and so you won't get an analytic function. Okay, so anyway, so by this definition, what you want to do is take a linear combination of these guys and its complex conjugates such that they satisfy these properties. If they satisfy these properties, those modes are positive frequency modes, and so they define the Minkowski vacuum state. If you wish, there will be a linear combination of these positive frequency Minkowski modes, but they won't be equal to the positive frequency Minkowski modes. But they define the same vacuum. You can take, it will be a linear combination of this, of phi k's. So that's what we did see. So UK bar R. we write this in the last lecture?
Yes.
Okay. So, you construct these modes in this way. First of all, they're normalized in the right way, so that they satisfy the right commutation, they're orthonormal. They have unit norm. And, well, they're constructed in a way so that they're analytic and bounded in they're analytic and bounded in the lower trains. Therefore, they're positive frequency modes, lower U and V planes. They're positive frequency modes with respect to ddt. They're not positive frequency Minkowski modes, but they can be written as a linear combination of positive frequency Minkowski modes. This means that they define the same vacuum state. So phi k and these guys define the same vacuum state, which is a Minkowski vacuum state. So what do we mean by this? I'm going to expand the field in terms of these modes and the complex conjugates. These are a complete set for positive frequency modes, but a general solution will have negative frequency modes as well. As I say, you need both of them to get a basis, to get a complete set of positive frequency modes, and you also need to include the Hermitian conjugate of that to get a full solution. So the Minkowski state, which was defined as annihilated by the Fourier coefficients we're expanding the field in terms of these modes, these positive frequency Minkowski modes, is also equivalently defined by being annihilated by the coefficients of these guys. So the great advantage of the way we've done it is that now we immediately have the Bogoliubov coefficients. The alphas are the coefficients of this guy, the betas are coefficients of the complex conjugate. So the B, this guy, we're covering the definition of Bogoliubov coefficients. Okay, so let's see. Well, first thing is, you can write this as in the following way. You just write the shine as the sum of the subtraction of the exponentials. And this guy here can be written like this. Okay, so now we want to the inner product of phi and phi bar r. So it's going to be So there's not going to be any contribution from this guy or this guy because ULK bar does not contain any phi bar R. It contains phi bar R star, phi bar left. So the inner product between phi bar R and any of these two will be 0. This guy, U R star K bar, similar thing. It will contain phi R star, whose inner product with phi R is 0, and some left modes, whose inner product with phi R is 0. Okay, so these guys will not contribute. Will have a 0 inner product with phi R. Now let's look at this one. This one, only this guy will survive. Because this is a left, and the inner product between a left and a right mode is 0. Okay, so I'm going to take common factor exponential of pi omega bar 2 alpha 2 shrine pi omega bar alpha 1 half and well, let me take this with inside here pi omega bar 2 alpha and then just this coefficient like A or K bar. Okay, so I'll call this 1, and this is coming from the term 1. Now the other one, 2. UL star. So there will be no contribution from this one because this is an L mode. The inner product with the R mode is going to be 0. But there will be from this one. Okay. Now I want to change the sign of minus. We've got a minus K bar here. I'm going to change that. So we're going to have this. So inner product of phi. I'm looking at this term. Is term 2. So A complex conjugate of this. So A L K bar complex conjugate of the complex conjugate is just the dagger. This is a Hermitian conjugate. And then this thing here, and only this one. So that's going to be, we want the complex conjugate of this. Now this is real valued, there's no i's imaginary units here, so that's still going to be this, and now the complex conjugate of this Any questions? So now what I'm going to do is I want to change the sign of this key. Sorry, this should be k bar primed. It's an integral which has nothing to, this k bar has nothing to do with this k bar here. Okay, the k bar here is a, the k bar here in the left entry is a dummy index. So this is k bar. And this is just, this k bar primed. Call it something else, different from k bar. And now I want a plus k bar here, just to make things a little simpler. So I'm going to change the sign of k bar. First of all, you can take out all this lot, you can take it outside. So this is now I'm changing the sign. I'm changing k bar primed to minus k bar primed. And I'm still calling it k bar. So that doesn't change the sign of this. It changed the sign here, minus. It does not change the sign of omega bar. Omega bar primed is just the absolute value of k bar primed. So if you change the sign, it's not change of k bar, it's not change the sign of omega bar. Same thing for the two shine. And now I've got this. And this is just delta of the two of them. That allows us to go through the integral. And so we have this.
Why shouldn't you change the sign of decay bar?
Decay bar? It does change it, but you change it here as well. So you have this. Now change it to something else. K bar minus k bar primed. You change it here. When k bar prime is equal to minus infinity, this guy is equal to plus infinity. When it's equal to minus infinity, this one is equal to plus infinity. And now you just change the order. You just change the order of the two of them. Okay, so that's the contribution from the second guy. This. I'm missing two alphas everywhere, obviously. And here, it's not primes anymore because I've gone through, it tells you the only surviving primed is the non-primed. So this shouldn't be primed. the shine, let's just take it outside common factor. And there's a minus missing here. Second term, and that's an important expression. Any questions about this expression? Or the derivation? Okay, you can do the same thing, not with the R, but with the left. The modes concentrate on the left wedge. Okay, I'm not going to do it in detail. It follows in a very similar way. You just swap the R's and the L's. So, like I've said many times at this stage, the fact that these annihilation operators of real particles includes creation operators of Minkowski particles tells you that the vacuum states defined by the two of them are not equivalent. So this is the number operator of real particles in the right real wedge. So you want to know.
Actually, this is the what's the Minkowski vacuum? So this is actually the number of particles zero in the vacuum.
Which one?
In the Minkowski vacuum.
Does anybody know the answer to Kessler's point?
This is actually the number of particles in the Minkowski's, the number of particles in the Minkowski vacuum.
This is something like an observer in the right Ringler wedge,
Or
five.
actually B. Oh,
Is it?
okay.
Let's forget about observers. It is important, what you said is correct, but I haven't explained why it's correct. Although I might have said it, I haven't really gone into detail about observers. Still, Hans's question, without referring to observers, Hans's question holds. Why is this not, if this is the number of particles in an constant vacuum state, why is this not zero?
Because you are using the number operator, and the Hilbert space where the number operator is defined has a different vacuum.
Exactly. So this is really the most important point out of, I would say, out of the whole course. You have you choose two different sets, complete sets, two different complete sets of positive frequency solutions. When I say positive frequency, they're defined with respect to different times. One is defined with respect to t, the other one is defined with respect to beta. But they're still, by taking those positive frequency solutions and their complex conjugates, that's a complete set of solutions in the whole complex space of complex solutions of the Klein-Gordon equation, of the homogeneous Klein-Gordon equation. So you can take either complete set of, we define the phi case, your positive frequency with respect to the phi k's and the phi k complex conjugates are a complete set of solutions of any complex solutions, arbitrary solutions of the Klein-Gordon equation. Okay? This is complete set. You can write the field any arbitrary solution of the Klein-Gordon equation as a linear combination of this. But this gives you a split into two sets of modes, the positive frequency mode with respect to ddt and the complement of that. And now you can do the same. You can, instead of using the phi case, well, you can use, like Joao says, you do a linear combination of these guys Hermitian conjugate, and so this defines the Minkowski vacuum state. You see, that's my definition of Minkowski vacuum state. It's the state which is annihilated by the Fourier coefficients as operators when you expand the field in terms of these positive frequency modes, which are positive frequency with respect to ddt. Now, you can do the same with these guys. You can say, okay, now I've got the UKs, R, and UKLs. They're positive frequency with respect to ddt as well, because they are analytic among the lower U and V planes. And we've seen that that's a defining property of positive frequency with respect to ddt. You can do the same. You can say I've got UK, R, UK, L, and the complex conjugate of that, UK R star, UK L R star. This is a complete set of any arbitrary solution of the homogeneous Klein-Gordon equation. So you can do the same thing again. Phi, now you call it UK R, and I've called it A R K, and ULK, and the Hermitian conjugate of this. And this defines a vacuum. This annihilates the state which is annihilated by these operators defines a vacuum. What vacuum is it? It's written on the board. It's written on the board.
The same Minkowski vacuum.
It's the same Minkowski vacuum.
Oh,
It's written here.
As it is the U
These guys are still positive frequencies with respect to DDT. It's just a different basis. It's a different basis which does not mix. These two guys are a linear combination of only these guys. They do not include any complex conjugates. And so these guys and these guys define exactly the same positive frequency space, same space of solutions. These guys are just linear combinations of the positive frequency modes. So it's an Minkowski vacuum. Again. And now you do it with what they've called these guys. So phi bar, R, A bar, and the left. Now these are not positive frequency with respect to DDT. They're positive frequency with respect to DD eta. Well, DD eta in R and minus DD eta in L, because remember DD eta in L goes down, so we want something that is future oriented. So you can do the same thing now. You can define these and their complex conjugates define a complete set of solutions to the homogeneous Riemann equation. So this defines a new positive frequency, space of positive frequency solutions. There's not the same as this P. It's some other, let's call it P and this is the complement of that. So they're really defining different Hilbert spaces. And as we've just seen, these guys are not just a linear combination. These positive frequency modes are not just a linear combination. These positive frequency modes with respect to DDT are not just a linear combination of the positive frequency modes with respect to DD eta. We see it here. They involve complex conjugates and so involve negative frequency modes with respect to DD eta. So whenever you expand the field now in terms of these guys, we call them B's, anti-Hermitian conjugate, the vacuum state that this Fourier coefficients define is not the same as this vacuum state. It's the Riemann vacuum state. As I say, they're not, these Riemann and Minkowski are not equivalent because whenever you write this in terms of this complete basis, this complete set, you need to include also the complex conjugates. This tells you that the betas in the Bogoliubov coefficients are not zero. And so, they're not the same vacuum. So just rephrase it. When you ask the question, you say, okay, how is it possible that the Minkowski vacuum contains any particles? It's because when you say this, you have to say which particles. Are they Minkowski particles or are they Riemann particles? Are they particles which are created by B dagger? Are they particles which are created by B dagger, which are Riemann particles? Or are they particles created by A dagger, which are Minkowski particles? And here, we're looking at the number operator of Riemann particles which are created by the B's, which are the Fourier coefficients when you expand in terms of the Riemann modes, positive frequency Riemann modes, positive frequency with respect to dE eta. So this is the number operator of Riemann particles in R, in the right Greener wedge, because these guys are 0 in the left Greener wedge. What if I calculate this? What is this equal to?
It's only 0, isn't it?
Why?
Because creation and annihilation operators are associated with the Minkowski.
Exactly. So this is the number of Minkowski particles, number operator of Minkowski particles. We're looking at how many Minkowski particles that the Minkowski vacuum state has, by definition 0. Okay? It's defined as in that way. So this is 0. But now we're not looking at the number of Minkowski particles in the Minkowski vacuum, we're looking at the number of Greener particles in the Minkowski vacuum. This is the sum of the betas. When we did the general formalism, it's the sum of the betas of the volume of coefficients beta. Okay, so we're acting. Okay, I've just deleted it, but real right one, it just swap R and left. So now you act upon the Minkowski vacuum. Okay, and use this, that Minkowski vacuum is annihilated by these guys, so this will give you 0. This does not annihilate the Minkowski vacuum, it creates a part of the Minkowski vacuum. So you're going to get, you're going to get the same from this guy as from this guy. So you're going to get exponential of minus pi omega bar alpha over 12 squared, because one from this one and the other one from this one. This is going to be squared as well, so 2 shine, and that's it. Okay, it's the square of the coefficient of this curve. This creates a one particle state, one particle Minkowski.
These R, A, R, and A delta are exactly the same.
Sorry?
The A, R, A, L, when act with M, are the same number with A without R or L acting M.
No.
So it's
Okay, I'm not sure about this. No, I don't think so, no.
so okay.
All that matters is that this creates, this acting upon M creates the same state as the remission conjugate of this acting on the bra M. And that state is normalized to unit. And this is okay. type of spectrum is this?
This looks like a Fermi.
Fermi?
That's it. And it's like the black body.
Okay, but not for fermions, for bosons. For fermions we have a plus.
Yes.
So we say that the Minkowski vacuum contains a thermal bath of real particles. Because of this Bose-Einstein distribution. Real particles at a certain temperature. Now Bose-Einstein excuse me. So you can read off the temperature, this is the frequency. The coefficient of the frequency will give you the temperature. So this is the temperature. So Kb is the Boltzmann constant. And here we're storing units. So you can just read from. So something which Joao pointed at, and I haven't really explained properly, but which was correct, but I haven't explained properly, is that a real observer will actually measure when the field is in the Minkowski vacuum state. The real observer will measure this amount of particles. So the vacuum state of a real observer is the real vacuum state. When the field is in the real vacuum state, the real observer will measure no particles. Okay? So the real observer always measures particles with respect to the real vacuum state. I haven't proven this, but this can be found in the literature somewhere even. I haven't done particle detectors. That's the reason why I'm only mentioning it. If I have time at the end, I'll go into it with more depth. Now, one issue is this is the temperature. So we've defined positive frequency modes. These guys are positive frequency modes. These ones were proportional to this. So there were really this frequency omega bar with respect to eta. Eta is not quite the proper time of the real observer to really look at the proper at the temperature of the bath of real particles that the real observer will see when the field is in the Minkowski vacuum state. You want to look at the frequency not with respect to the eta, but with respect to the proper time of the real observer. So let me write this. We use modes. proper time.
Exponential to minus.
I wrote this quickly because we've done this. Exponential minus I omega bar eta plus I k bar zeta. So, an actual renal observer would measure a similar thermal mass but with a temperature given by the following. So we have omega bar eta. Okay. Using the relationship between eta and proper time. This is equal to this. So the frequency of the frequency as measured by the Wiener observer really is the coefficient of the tau bar, which is not omega bar, but it's equal to this. I call it the omega r. So now you go back to your thermal factor. And the temperature now is given by this. So in terms of the frequency as measured by a Wiener observer. And this is really the acceleration. If you go back to the notes, what we did at the start of Wiener observers, this is the acceleration of the Wiener observer. As I say, I haven't really explained this. I certainly haven't proven this. That the Wiener observer really measure particles with respect to the Wiener vacuum. It is kind of natural, but I haven't shown this. So just to finish off, flat spacetime, just to tell you, well, some people question this, by the way. Some people question that the Roux effect is not a physical effect. It hasn't been measured, because you would need to go to very high accelerations. So just to get a feel for this. acceleration. So to get a temperature of 1K, which is still lower than the CMB temperature, you would need something like this, and this is less than the acceleration of electrons in the at Stanford. Any questions?
Is the acceleration process non-unitary then? I'm an observer in a flat space-time, so there is nothing outside the universe by assumptions. And suppose that I use some energy, some mechanism nearby that is also part of space-time and starts to accelerate. I will measure some particles, some Ringler particles. These particles present the thermal spectrum. So I would say then that the Minkowski vacuum state is a mixed quantum state. So while I am accelerating, the Minkowski vacuum state starts to look more and more mixed. Why is this the case?
Why is it the case? Nature does what it does. Why? It depends on what you mean by why. One is people say that it is whatever engine is accelerating the observer that's really creating the particles. So that's one way of looking at it. The mixedness comes from the fact that a real observer does not see, is constantly disconnected from the yellow wedge. So that's really how, in some sense, if you wish, you're tracing out the left wedge in order to get a thermal fate. So another thing I wanted to do is to go into density matrices and express the group, the Greenberg state in terms of Minkowski state and so on. I'm only going to do this at the end. If we have time at the end, I'll go that into the density matrices and particle detectors, so two things I would like to do. But only if we have time at the end. But the degree is coming from this. So that allows me to seek the equivalent of this in curved space-time. What is the equivalent of a real observer in curved space-time via the equivalence principle?
Free fall. Larger disks. Free fall.
We are. The Earth's pushing us towards it.
Sorry?
We are, in some sense.
Who's we? Right now?
Yes, we are under the effect of the gravitational fields of the Earth. So we could take out the Earth and accelerate ourselves.
Sorry? So, yeah, I'm only talking locally.
So then The ones that are accelerating instantaneously before.
But what's the equivalent of linear observers in core space then? Sorry?
Gravitational field.
But what are the observers that are equivalent to linear observer?
Inertial observers in gravitational field.
Do we just
In what
take,
sense you are
just we take the motion, equation of motion, and then uses quantum acceleration?
Can you define equivalent in that case?
I would say yes.
Then one that observes, locally observes the same. You can't distinguish locally between a linear observer in flat space-time and what observer in core space-time.
The ones that have the same gravitational field instantaneously.
It's a free fall. This is the equivalence principle.
Oh, are you?
I explained this at the start as well.
I
know it as well.
A standing still observer in some gravitational field.
In a constant gravitational field.
Sorry?
Constant gravitational field.
We've got a linear observer in flat space-time. Okay? Now let's consider another setting, which is there is a gravitational field. It's not flat space-time. There's some gravitational field. What observer will locally see the same as the linear observer in flat space-time? Let me ask you a different way. What about inertial observer in flat space-time? What is the equivalent of that? By equivalent, I mean that locally we'll measure the same things. We'll see the same laws of physics. What is the equivalent of this in core space-time?
Any observer that's following the geodesic timeline?
Exactly. So, free-falling observer in core space-time. Observer that's following a tangent geodesic. So this is a Minkowski observer with inertial. What is the equivalent of a Wheeler observer in flat space-time?
The other ones. The ones that are not following geodesics.
Well, there's many different. So, right, okay. So that's right. That's roughly right. Wheeler observer in flat space-time with a certain acceleration a, you need to go to an accelerated observer in core space-time with the same acceleration, the same acceleration a. Not just any arbitrary acceleration, it has to be the same acceleration. So locally we will measure the same things. That has to be very clear. Just equivalence principle.
The issue that makes it confusing might be the fact that in curved space-time, the acceleration in curved space-time is, the mathematical definition is a little different from what in constant space-time, flat space-time.
General relativity tells you gravitation is not a force as such. It's the curvature of the space-time. So, observer just free falling just means following, the curvature of the space-time as produced by the gravitational field. So those observers are not accelerated in core space-time. They're just free falling. They're just following geodesics. They're not accelerated. So they are the equivalent of inertial observers, constant velocity observers. This constant velocity in flat space-time. This constant velocity. The observers which are not following a geodesic in core space-time, they are accelerated, and they're the equivalent of accelerated observers in flat space-time. Okay, so if you go to the black hole case, you also have a causal disconnection between what's inside the black hole and what's outside the black hole. if you have an accelerated observer in a black hole spacetime, which means not that it's just free falling, it's not following a geodesic, it's static, say, it's just inside the black hole sitting with an engine that keeps it at fixed spatial position, so it's not free falling, it's accelerated. That observer is the equivalent of the Wiener observer, and so it's the equivalent of the Wiener observer. And so you will see, in principle, you will see particles in near a black hole. Okay, so let's do coarse spacetime.
If people question the Aula effect, why don't people also question Hawking radiation or do they?
I don't know if they do or not. I've only seen the on-row effect papers. There's one technical detail that I glossed over, which is the zero frequency modes. Zero frequency modes. So they claim that the zero frequency modes, not considering the zero frequency modes in what we've done, which I haven't talked about, invalidated. And there was a toing and throwing. Belinsky, I think that's Belinsky in his group. There's a toing and throwing between Wald, Unruh, Fulling, and the Belinsky people. But it gets quite technical. You're welcome to go and look at the papers. Okay, so curved in cross section. So a lot of what we've done already in flat spacetime carries over in coarse spacetime. So first of all, canonical QFT in coarse spacetime. So we're going to consider globally hyperbolic spacetimes. This means that there exists a Cauchy surface, and it can be proven. It also means that you can foliate your spacetime based on some parameter t. So the parameter t is just labeling, if you wish, the different Cauchy surfaces. And we consider, again, a real scalar field massless, well, for now it is mass, so scalar field which satisfies the Klein-Gordon equation in car spacetime. Okay. Psi is the coupling constant. R is the Ricci scalar, and N is the mass of the field. So we can define a current this is a conserved current if phi 1 and phi 2 satisfy the Klein-Gordon equation. So the divergence of field